so we need to just flip. So is that full screen now? Is that okay?
That's perfect.
Okay. All right. Yes. Thank you, Nico, for the invite to speak. I'm glad I finally made it, even though it's not in South Africa, but it's lovely to be here. However, I mean, given what Alfredo was saying before about measuring shapes and whether you can really measure shapes, I feel a bit like I'm on a hiding to nothing here. But I will tell you about some recent measurements we've been doing measuring shapes in neutron-rich 100 nuclei. But before I do that, I guess I couldn't resist the challenge, was just to show some pictures from when you were my PhD student at Brighton. For people who don't know, this is Nico in the bottom right here in all his finery at the University of Brighton, with the flat Brighton seaside behind him. And his PhD was on actually multi-quasi-particles and shape-driving effects. So there's the shape word in there already. It was based on some experiments that we did at the ANU in Australia. Here we are in Canberra with the late, great, and much missed George Drakoulis. So that's Nico and me. And then here we are actually in the garden in Brighton discussing the results with who we got here. We've got Dave Cullen, Carl Weldon, I think, and Phil Walker that you mentioned in that news clip you showed us as a recent recipient of the Rutherford Medal. So it's a real pleasure and an honor for me to actually be at your meeting, Nico. I think you've come great strides since, well, I wouldn't like to say how many years, but I'm really, really pleased to be here and see what great things you're doing. So back to the title of the talk, which is Shapes, Neutron-Rich Nuclei Obtained from Lifetime Measurements. As I say, I feel a bit of a fraud given what Alfredo says, but we'll carry on. And I guess the outline of the talk is just some motivation. Why do we want to do this? Why do we measure lifetimes? Why have we built an array of lanthanum and bromide detectors? And then just to show some results of recent measurements in the zirconium and palladium nuclei. And I'll touch briefly on plans for what we're going to do with Fatima at the FAIR facility. So why am I interested in this region? Well, this is a very simple plot, and I'll go simply, I guess, on the first few slides. I think we were asked to speak to the students. So the first few slides hopefully do that. We plot the very simple energy of the 4 plus of the 2 plus across the neutron-rich region from zirconium here in purple to molybdenum here in blue. We see a very strong shape change at around about n equals 59 based on just the energies. So one of the things we want to do is to measure the shapes of those nuclei. So why do we measure level lifetimes? Well, we know that the level lifetime here, this tau, is related to the transition probability. If the transition is an E2, then we have some energy dependence, but we also have some dependence here on the structure, the relative wave functions that we are connecting with this transition. The B2 gives us some information about the transition quadrupole moment squared. Notice this squared here. And up till this stage, everything is exact. The next stage, which is obtaining the deformation beta that we talk about from Q, is where it becomes model dependent. The relationship I've got here is for a quadruploid, but there are other formulae are around. But this is how we get to a deformation beta from a lifetime tau. But note that because we have this Q0 squared here, we can't get the sine of Q0, and therefore we can't get the sine of beta. Okay. So I see Julian shaking his head already, but I'm going to carry on. So why do we want to measure the lifetimes of levels in the sort of picosecond, nanosecond region? And for that, we want to use lanthanum and bromide detectors because they have good timing resolution and reasonable energy resolution as compared to germanium detectors. If we have very small detectors, we have a very good full width half maximum of the order of 200 picoseconds. If we have much bigger detectors with more efficiency, then the timing resolution is not so good. So it's a trade-off, as in all things, between resolution and efficiency. And the UK decided to build an array of 36 detectors, which we've called Fatima, which is a fast timing array of lanthanum and bromide detectors for use at FAIR. And this was proposed, and Luis Frail from Madrid led the technical design report for GSI, and that was submitted to GSI and approved in 2015, and the detectors were designed and built and the frame, etc., commissioned. So while we're waiting to do experiments at FAIR, we have done some other experiments elsewhere, and I will just give a little overview of those recent measurements. The first thing we did with the array was we took it to the RIKEN lab in Japan, and this is a Lego table of the isotopes, if you like, that's in the entrance hall at RIKEN, showing the binding energy basically of nuclei across the nuclear chart. We see here the black colored Lego blocks here, which are the stable nuclei, and then if you took a cross section across here, you get a parabola showing that as we get to more extremes on the edge, then the nuclei become radioactive and they beta decay. So the interesting thing we were studying here was the neutron-rich zirconium isotopes, where I showed you before there is predicted to be changes just based on the energy, the 4+ to 2+ energy levels. So what did we do at RIKEN? Well, RIKEN has a very nice series of accelerators that can produce a beam, and we were interested in a uranium beam. So we had a uranium 238 beam, 345 MeV per nucleon, which impinged on a beryllium target and made some fission fragments, which included the nuclei that we were interested to study. And they were separated by the big RIP separator and sent onto our target station. Now, I'm not going to give too many details of the big RIP separator, but there are other similar things at other labs around the world that people may be familiar with. But basically, it's a series of electric and magnetic fields, and if we set the fields to particular values, we can identify the A over Q of the nuclei that fly down the middle of the separator here. We can then install an ionization chamber at the end of the fragment separator, which gives us a measure of Z, which means that we can then identify completely the nucleus that has traveled down the separator. And what we do with this is we take our beam of interest, which is a radioactive ion beam, and we hit it on a stopper. So we stop it. We then wait for it to beta decay, because it's a fission fragment. Most fission fragments beta decay. And we start a clock. So we have a clock which measures the time between the beta decay and the gamma rays. And this gives us a measure of the lifetime of the levels that we make in the nucleus, which gives us a test of the wave function and therefore some indication of the shape of the system. We need something to measure the electrons, and we need something to stop the ions. And at RIKEN, we did this with something called Wasabi, which is a combination of an active silicon stopper array, which you can see in here with the green surroundings to the silicon. And then we needed something which gave us good timing for the electrons. So we used some beta plastics, which are these black pieces of plastic in here. And that gave us the time of the electron. We then need to measure the time of the gamma ray. And this is where our array of lanthanum and bromide detectors came in. We had a combined array, which had some germanium detectors, here, the rising clusters. But also we put in at 90 degrees to the beam, we put in 18 lanthanum and bromide detectors arranged in patterns of 6. So we see here 1, 2, 3, 4, 5, 6 along the line, and then 2 slightly off the 90 degrees. So the electron triggered the plastic detector to measure a start, and then the gamma ray triggered the lanthanum and bromide detector, and we measured the time between those two things. I show here on the next slide just a PID plot. So this is how we identify the nuclei. As I explained, we have a mass to charge ratio here, and then we have an atomic charge, and so we can pick out the nucleus that we're interested in. We were interested in zirconium 104 and 106, and they are produced by yttrium 104 and yttrium 106. I show here the PID, the product identification plot for yttrium 104. So we put a gate on this 104, and we look for the zirconium which has arrived from the beta decay. This is the gamma ray spectra that you get. So these are the quality of the spectra. The red shows the germanium spectrum, and this has been scaled down. And then in the blue, we have the lanthanum and bromide spectrum, where we see that the resolution, the energy resolution is worse, but that's kind of what we expected. But we do see the 2 to 0 here in the nucleus that we are interested in. So this is just a measure of the gamma ray energies. If we also do a plot of the gamma ray energies against the time at which they arrive relative to the electrons, then we see for our 140 kV transition here, we do see that there is a lifetime to this level, which when we plot and fit, we get a lifetime of the 2+ state of 2.9 nanoseconds, which is in good agreement with the previous value that was measured. So that tells us that the experimental equipment is working, and we're getting answers in the right ballpark. If we then move on to 106 and do the same thing, we see again a very strong 2 to 0 transition here, which has a time profile, and when we fit that, we get a lifetime of 2.65 nanoseconds with about 0.2 nanoseconds of error. We can use that information in the way that I described before to extract deformations. First of all, we have B2 values, and the B2 value we measure is very similar to the previous value. And then we can use our model to get the modulus of the deformation. And while this is not the complete information that you want, in this case it's quite useful just to have the modulus, because the Hartree-Fock-Bogolubov calculations say that if we have a shape change to oblate, then the deformation we'd expect would be about 0.1. And the deformation that we measure, the modulus of the deformation, is about 0.36, which means that based on these calculations, that we can say that the zirconium 106 remains prolate. We can also say that the n equals 64 is slightly more deformed than n is 66. So there may be that we've reached the peak of the deformation and we're starting to come down. But it's kind of early days to say that. I think we really want to be able to measure this next nucleus here, 108 zirconium, for which we know the level scheme, but we don't yet know any lifetimes. So that shows the information that we obtained at RIKEN on the deformation of the zirconium nuclei, which were measured using the lanthanum and bromide detectors. Want to move on now to the second set of data that I would like to present, which is some data that we got from the Argonne lab that we measured with gamma sphere from a Californian fission source. So what we did there was we took half of gamma sphere, So there's 51 detectors, which is shown here and also here in this bottom right plot. And then we mixed that with a hemisphere of 25 lanthanum and bromide detectors. We were able to do fourfold coincidences because of the number of gamma ray detectors that we had, and also because we were given quite a long counting period because we counted over Christmas. So this experiment is the first time that I've ever been in a lab on Christmas Day doing an experiment. We had about 3 weeks of data. It was good fun, actually. I enjoyed it, and some very kind people from Argonne were very hospitable, and they brought us some nice Christmas lunch, so it was lovely. We had a good time. So anyway, we were able to measure fourfold coincidences: germanium, germanium, lanthanum, lanthanum. Why do we want to do that? Well, from this data, we were able to get some information on palladium-114. I show again here the top picture just of the energy, the 4+ against the energy, the 2+, which is what I showed before, where we showed the very strong shape change in the zirconium nuclei at about 59, n equals 59. You see here, if we look at the palladium, it's essentially flat. The palladium nuclei don't have this shape change. If you take just the energy of the first 2+, you get quite a stable beta-2 deformation, but actually the palladium nuclei are thought to be triaxial. And triaxial, just for the students, just means that you have 3 axes which are of different lengths. So we have a long axis, a not so long axis, and a short axis. That's what we mean here by triaxial. And indeed, there are calculations by, hopefully I say this right, Luo et al. in 2018, which show the value of gamma for the palladium nuclei as a function of rotational frequency. And the one that we're interested in is this green one here, which has a gamma deformation of about -60 degrees. So that was the nucleus that we were interested in. If we look at the level scheme for palladium-114, we see a very nice ground state band here. We also see what we'd call it a quasi-gamma band here. And there's a very nice paper, 2005, from Stefan Fraundorf. I don't know if Stefan's on the call. I know he was earlier in the week, which says that if you look basically at the energy staggering of this quasi-gamma band, you can work out whether the nucleus is gamma soft or gamma rigid. The nucleus is gamma soft, then the energy staggering as defined here is positive for odd spins and negative for even spins. And on this plot here, the energy staggering for odd spins is the solid lines, and we see if we follow the solid lines that it's positive to round about palladium-114, and then it maybe goes negative or maybe not. So this analysis suggests that the lighter nuclei than palladium are gamma soft, and the heavier ones are gamma rigid. So that was part of the motivation for this work. Sorry. Okay, so this is some data that we collected. This is the quality of the data. As I said, we had fourfold coincidences. So in this case, this is the level scheme of palladium-114. We set germanium gates on these 4 transitions here, any 2 of them, and then we looked at the 520, the 4-2, and the 2-0 in the lanthanum bromide detectors, and this is the quality of the spectrum that we had. So the red is the germanium, which with the better resolution, and then the blue is the lanthanum bromide, which are wider, but we still see the peaks of interest. We show this in the projection of a cube where the third axis is the time. Then we see 2 blobs corresponding to the correlation between the 520 and the 333, and the 520 and the 333 both ways round. And we see also that we have some background that we need to take care of. So if we make projections and slices on this cube to get time spectra, then we end up with this plot here, where the black time spectra relate to the coincidences between the two gamma rays of interest. But then we have lots of types of background. We have a peak with a background, we have a background with a peak, and we have two backgrounds. And that's why we have 6 background spectra here that we need to shift and subtract from the spectrum of interest. When we do that, and we measure the time difference between these two black spectra here, we get a lifetime for this 2+ of about 113 picoseconds. So we see here that we've moved an order of magnitude. The zirconium we were measuring 1 or 2 nanoseconds. Here we're measuring hundreds of picoseconds. So there's a factor of 10 difference in what we're measuring, and this is really a test of the lanthanum bromide and how well it can do for very busy spectra. See here, these spectra are very busy because it's a fission source. So we have that data, which is for 113 picoseconds for the lifetime of the 2+. We can then work out a B2 value, which is this value here, and we've plotted it here as comparison with the cadmium isotopes, which are the open squares, which are probably good examples of just spherical vibrational nuclei. So the B2 is quite constant. For the ruthenium isotopes, which show gamma softness and stable triaxiality, we see an increase in the B2 values, and it's thought, I think, that the maximum of triaxiality in ruthenium is expected at n equals 68. That's a paper by Dan Doherty, who's our next speaker in this session. And then we have this work here, where we've measured for the palladium 114. Now we do see an interesting trend here in the increase in B2, and then we see this staggering effect, which could be interesting physics, but it's also true that these two values were measured from a fission source, and they were measured with the Doppler shift method, following with only singles. So when these two B2s were measured, then there was no feeding taken into account. So it could be that these lifetimes have been overestimated, which means that the B2 values are underestimated, and it would be of interest to go back and measure these things. So that's a measure of the B2. What does that tell us about our shape? Well, I plot on the right-hand side here a value of the B2 2:0 and the 4:2 ratio, and this is the value that we measure here for the 114 palladium, which is lower than all the model descriptions that we have here, but it is consistent, at least one would say, with the rigid axial line, which is this dashed line here, which would be consistent with this palladium undergoing 114 undergoing a transition to a gamma rigid nucleus. However, I mean, what we've measured here is just the ground state band, and what we'd like to do is to measure the quasi-gamma band, and we have a proposal to measure that using Culex at Caribou, which I hope we will be able to do. So I realize that my time is coming short, but I just wanted to just give a PR bit, if you like, for what we're doing at FAIR. I said right at the beginning that the UK built this array to be used at FAIR. And FAIR, for those who don't know it, is an extension of the GSI facility with a new accelerator and lots of new beamlines and lots of new experimental areas, which will take us to increased energy and increased intensities. We built the array. This is a picture of the array at GSI in March this year. This is the group of people who assembled it. We see Jolt here. I think Jolt's on this meeting. It was all ready to run. We had a schedule. And then something happened in March that we're all aware of that meant that these experiments got cancelled. But we were able to complete this first experiment, which was led by Paddy Regan on palladium 94. And that has went well and shows that the system is running. The two experiments that we weren't able to do have been rescheduled and are now moved to 2021. So we're hoping to get to do them this year, either remotely or hopefully in person. So that's just a quick overview of what we've been doing with our lanthanum bromide detectors. I guess my thanks go to the Fatima collaboration, which are listed here. My apologies if I've missed anybody. Luis Frail was the one who did the TDR document for GSI FAIR. My thanks to Frank Brown for his analysis of the RIKEN data, and to Eugenio Gamba for the analysis of the gamma sphere data. Thank you very much. Ooh.
Can I make a short
I'm not
comment?
sure. I seem to have lost contact. I've stopped sharing my screen. Is anybody there?
You have to entertain everybody for a while, Alison, I think, till Nico comes
Nico
back.
has just lost contact for a moment. He'll be with us shortly.
Ah, right, okay. I don't know if there are any questions in the chat. I could share the chat myself.
Can I say few comments, 2 comments to your talk?
Yes, Julian, I saw you shaking your head really early on.
Yeah. Well, the first, I'm very glad to see you in good mode. So after many years.
Yes, it's nice to see you.
Sure. So I have two comments. One experimental one.
Yeah.
You are great about this lifetime measurements in gamma smear when you have a lot of scattering between germanium and so on, and the background is terrible. So that you overcome it, it's just great, because we measure in Warsaw with such advice with just Fatima and germanium detector. We got so many artificial lifetime that it's a real problem. And then when you go to your one of the first slide about Q0 formula, when you connect Q0 to lifetime,
yeah,
I think it's too big simplification. It's formula from axially symmetric rigid rotor. So particularly when you talk about triaxiality, so you have to be very careful. That's all. Thank you.
Yeah, no, you're absolutely right. The formula that I give at the beginning, I probably didn't explain it properly, but I could do that for the maybe for the students, just to clarify what your. Can you see that?
Yes.
Formula, yeah. So yes, you're absolutely right. I mean, it assumes axial symmetry. It's a very simple formula, and it's appropriate for the. Well, I think it's appropriate for the zirconium nuclei that we measured.
But when you found that the ratio energy of 4 to 2 is about 3.3, then in some way it's justification of this formula.
Yeah. So we've assumed something going from here to here. That's right. Yeah. Okay. Yes.
Is there any other questions? Okay,
Sorry,
there's
Alison,
no more questions.
I lost contact. Yeah. Sorry, I lost contact. I have too many windows open here. Can you hear me now?
Hi, Nico.
Hi there. So everything is okay with the questions?
Yeah,
Anyone?
I had a question and a comment from Julian.
All right, excellent. Julian did the ruthenium 104, so he's keen on that one.
Yeah.
So, okay, so if there are no more questions, Alison, I thank you very much for everything. It's been 20 years since you came to pick me up at Gatwick Airport. So it's been a while, but we haven't changed too much.
You're a very generous man, Nico.
You look
very
exactly the same.
Okay, thanks.
So,
Bye.
all right. Thank you so much. A round of applause also for Alison.